With our full structural formulas from the last video, there are 3 structural isomers of pentane, so C5H12. C5H12 is pentane, all singly bonded carbons. The most simple one is plain old pentane, where I have 5 carbons in a row and the hydrogens going around. The boiling point of that is 36.3 degrees Celsius. Then I can basically lop off and move one of my carbons over, so I have a CH3, CH, CH3, so that CH3 that's in parentheses there is coming off of that carbon, CH2, CH3. That one is actually called 2-methylbutane. So on my second carbon, I have a CH3 or a methyl group coming off of it. And the boiling point of that is 27.9 degrees Celsius. Again, we're seeing the more round we get, the lower the boiling point is. And then I can go one more structural formula. I have a CH3C with 2 methyl groups coming off of it. That's what it means here with the CH3 too. 2 methyl groups come off of this carbon, followed by a CH3 at the end. This one is very round. It's called 2,2-dimethylpropane because I have 2 methyl groups coming off of the second carbon. And the boiling point for this one is a mere 9.5 degrees Celsius. Okay, I want you to do hexane. Hexane is generally the largest that IB will look at. So take some time, pause the video, go through what different isomers you can get of hexane. And go through naming them, because if you can name them different names, that means that you've done them correctly. If you've put something off on a side and you're like, oh, this is a new one because it looks different, but it's actually the same name, then it's not a different structural isomer. So go through that. And then we get to the first common reaction that alkanes undergo. We know that almost all organic compounds are flammable and oxidize when burnt in air. Burning in air means that it's reacting with the oxygen. We have some spark, some sort of energy that's going between the oxygen in the air, the O2 gas, and the organic molecule that we're dealing with. So we must have plentiful O2, a lot of it, otherwise the reaction will not go to completion. And one of the most common ones that we're going to see in this world is octane. So C8H18 reacting with O2. And if you remember from last year, the 2 products in any combustion reaction is carbon dioxide, CO2, and water, H2O. So you can go ahead and balance that one at this time. When you're done with that, you can click play again. And the reason we dealt with the octane is because that's something that will probably come up on an exam because it has a real-life application. Octane is a common source of energy in our society. So how many different isomers of C5H12, in other words pentane, exist? You're correct if you got C, 3 of them. Good. So back to our combustion reaction. Alkanes are generally chemically unreactive. Something's got to happen to make that reaction happen. And when we're looking at the reaction, a combustion reaction, the only reason that it's occurring is because we have something that overcomes the large activation energy. Remember that a capital E lower subscripted A means activation energy. That large activation energy has to be overcome, and then we actually get stronger bonds in our products. So in our reactants we have carbon-carbon bonds and carbon-hydrogen bonds, which we know are strong. But we know that the carbon-oxygen and oxygen-hydrogen bonds in the carbon dioxide and water are stronger. Therefore, their enthalpy is less than the reactants were, which means it is exothermic or releasing energy. And this is a reminder of an energy level diagram. So the enthalpy or the energy of these is higher in energy than the products, reactants going to products. This is my activation energy. It takes a lot of energy to overcome to get to my products. And the delta H value, or the change in the enthalpy, is a negative value, and that means that it's exothermic. If there is not enough oxygen, then we've got some problems. The combustion won't go to completion, and we get a whole lot of side products. We still get carbon dioxide and water, but we also get things like carbon monoxide and carbon in the form of soot. And there are other possible pollutants also based on what other things are around during the reaction, which would make balancing really difficult. So it is always good to write on your examination that you are assuming that it is a complete combustion reaction, or that the reaction goes to completion, and then it's much more simple to balance. And this is generally what happens in a combustion engine. So know these possible side products. Those are going to come in handy if you see a multiple choice question or a written section on paper 2 saying what possible products could you get if a combustion reaction does not go to completion. But if you are ever given a problem where it says determine the products of this reaction and balance it, then make sure to write down that statement. I assume that this goes to completion. Another common reaction for alkanes is called halogen substitution. We know that the halogens are in that 7th column or 17th column, depending on how you're looking at the periodic table, and it's going from fluorine down to astatine. Now we know fluorine is not something that we want reacting with hydrogen because we get hydrofluoric acid, so the majority of our halogen substitutions that we're going to look at are with chlorine substitution. And these reactions require UV or ultraviolet light or very high temperatures to overcome the activation energy. And basically what happens overall is, I'm looking at a ethane here, we'll look at methane in a little bit, but in my ethane reaction I have 2 carbons bonded together with 6 hydrogens going around and Cl2. What happens is the Cl2 gets broken up by the ultraviolet light, and we know that that is very electronegative. We have a radical Cl, chlorine ion. It's going to really want to bond with something, so what it does is it comes in and takes the hydrogen from the ethane, and then that leaves the other radical chlorine to bond to that ethane. So I have a chloroethane now instead. And we could keep doing this, so we could keep getting UV light coming in and breaking up chlorine into radicals, and then they can keep cleaving off those hydrogens, and then we end up replacing more than one hydrogen. So for instance, I could get C2H5Cl2, it's taken off 2 hydrogens and replaced 2 chlorines, and we could call that 1,1-dichloroethane or 1,2-dichloroethane, depending on whether they are on the same carbon or if they are on one on each carbon. And I could go all the way up from having 1 hydrogen replaced to having all 6 hydrogens replaced, in which case I would call that hexachloroethane, and I'd have a formula of C2H6 with the, or C2Cl6. All of the hydrogens have been replaced by chlorines. And this all happens by what is called the free radical reaction chain. So what is the process? The first step in this is called initiation. In an initiation part of the process, that's initial, the beginning part of it, what happens to make it happen. I'm being initiated into this process. It produces the radicals in the first place. So my UV light comes in, breaks up my chlorine gas into chloride radicals. And then step 2 is that those chloride radicals propagate. Okay, we're going to continue this reaction for a long time potentially. And by long time I mean many things happening, not necessarily the space of time in which they are happening. These reactions happen very quickly, so overall span of time is not what I'm discussing here. The products and further radicals are going to be formed, and this can go on for many, many molecules. So for instance, I'm onto methane now instead of the ethane that we were last looking at. The chlorine radical comes in and cleaves off the hydrogen, leaving hydrochloric acid and a methyl radical. So I have a new radical now that's going to react with something else. For instance, that methyl radical could react with a chlorine gas molecule and cleave off one of those chlorine gas molecules to form a chloromethane and a chloride radical. And this process can keep going on for as many molecules as they are for however long it could take, forming all sorts of products. Step 3, though, is when we come to termination, or we are terminating the reactions, and all of the radicals are consumed and no further reactions occur. For instance, I could have two chloride radicals forming more chlorine gas, or I could have a chloride radical and a methyl radical forming a chloromethane, or I could have two methyl radicals forming an ethane. And now I have all of my reactions terminated.